Hello everybody, getting ready to do lesson 8.1 part 3 today, classwork, pre-calculus math. And today's lesson, sequences and series part 3. You got 6 points here in your notebook and 40 points here will go into your classwork sheet. Have your classwork sheet ready to go, students. Name, date, period, and if you're taking this online, put your due date here for that. And today's bell work, students, teachers, find, if possible, A, B, C, and D here. Here's your A, here's your B here, so do that. And I'll give you 5-6 minutes for that. Okay, welcome back everybody for your solutions for today's bell work. For A here, which is A minus B, this matrix minus this matrix, you get this matrix here for A minus B. And then for B, which is 2B minus 3A, 2B minus 3A, you get this matrix here for that. And then for C, AB will be this matrix here, A times B. And then for D, which is BA, B times A, you get this matrix here. In lesson for today, and we have a notebook slide here, summation notation. There is a convenient notation for the sum of the terms of a finite sequence. It is called summation notation or sigma notation because it involves the use of the uppercase Greek letter sigma written as that. Definition of summation notation: the sum of the first n terms of a sequence is represented by this representation here, sigma n over I equals 1, a to the I, which equals a1 plus a2 plus a3 plus a4 plus a to the n. Where I is called the index of summation, down here your index is here. N is the upper limit of your summation, and 1 is the lower limit. I'm sorry, this is 1 here, I equals 1. So 1 would be the lower limit of your summation, would be here. This would be your upper limit, and then this would be your I here, which is called the index. So sigma notation for sums. So in this situation here, we have the summation of 3i with 5 is the upper and 1 would be your lower limit for that. And we start with 1, 3, 2, 3, 3 times 2, 3 times 3, 3 times 4, 3 times 5. And that would equal 45. And then for B here, our upper is 6, our lower is 3. And then here's our index, 1 plus k squared equals what? So when we plug in, we start with 3, 4, 5, and 6. When we sum all that up, we get 90 here for this summation there. And then for C here, our upper here is 8, and then our lower is 0, so we start with 0, and then it's 1 over n, factorial n, and then this will be your array here of terms for that. And then when we sum all these together, we end up with 2.71828, which, by the way, is very close to your rational number of e, which equals 2.718281828. It can be shown that as more terms of the sequence whose nth term is 1 over n factorial n are added, the sum becomes closer and closer to e, by the way. So let's try one here. Find the summation here, students. So for this one here, upper limit 5, lower limit 1. Here's our index here, 2i plus 1. So when we plug in, we start here at 1, and then we go up to 5. So 2i plus 1, it'd be 2, 1. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. 2 times 5 is 10. We add all that up, we get 35 for that one. I'm going to let you do this one on your own, students. In example 8, note that the lower limit of a summation does not have to be 1. So in this case here, k would be 3 here in this situation. And then our upper is 6 there. Also, excuse me, note that the index of summation does not have to be a letter I. So it does not have to be the letter I. For instance, in part B, the letter K is the index of summation. So we got K here. Properties of sums. So here's our summation here. Summation C equals Cn. C is a constant. And 2, we have upper limit here, lower limit, Ca to the I. And then we can pull our C out here. That's almost like a calculus move there. C is a constant. And then for 3 here, upper limit, lower limit, and then here's our I here, and then you can do this property here, and then do this property here for this one. Okay, so for series, many applications involve the sum of the terms of a finite or an infinite sequence. Such a sum is called a series. Definition of a series: consider the infinite sequence A1, A2, A3 up through AI. The sum of the first n terms of the sequence is called a finite series, or the partial sum of the sequence, and is denoted by A1, A2, A3, An. By this situation here, n will be your upper limit, and then I would be 1, a to the I. The sum of all the terms of the infinite sequence is called an infinite series, and is denoted by this here, where you have this symbol up here. Your upper limit would be your infinite symbol, and then your lower limit would be 1, and then a to the I. So let's try an example here. Example 9, finding the sum of the series. This series here, this is infinite series. I equals 1 be your lower limit, and then 3 over 10 to the I. So A, find the third partial sum, and B, the sum. So okay, the third partial sum. So the third partial sum is your upper limit would be 3. You start at 1, so 3 over 10 to the 1 plus 3 over 10 to the 2 plus 3 over 10 to the third power. That comes out to 0.333 here. 3 over 10, 3 over 100, 3 over 1000. This gets to be 0.333. Okay, the sum of the series, where upper limit's infinite, we start at 1, 3 over 10 to the I. So in that situation here, we just keep adding out here, and we tend to approach a single number here, which is again 0.3333, which is 1/3. This keeps getting smaller, smaller, smaller. So your increments of addition are pretty small, and we eventually end up here at 1/3. Okay, so in this one here, find A, the fourth partial sum. This will be our A, and B, the sum of the infinite series here. So this is our upper limit is infinite. Our lower limit here would be 1. And then here is our index here, 6 times 1 over 10 to the I power. So a partial series here, the fourth partial, will be this 6 over 1 over 10 plus 6 over 1 over 10 squared, cubed, and then fourth power. And then this eventually settles on 0.666, which is the same thing as 3333 over 5,000. So that would be your fourth partial sum, and then that's up to you, students. Let's go into another one here. Population in the United States. From 1980 through 2008, the residential population in the United States can be approximated by this model here. And then n equals 0, 1, 2, and it goes on up to 28. We start at 1980, we end at 2008, so we got a 28-year span there. where A to the n is population in millions and n represents the year, with n equals 0 being corresponding to 1980. So 0 hour will be 1980. Find the last 5 terms of the finite sequence. So the last 5 terms of this infinite sequence are as follows. So the last 5 terms, 824. So we start at 24 because we're going up through 28, right? So we start at 24. So we have, this is our 2004 population. When we plug this into our, basically our function there, we get this number. And then our year 25 would be this number here, 296.7. And then our year 6 would be this number here, 299.9. And then our year 7 would be 303.1. And then our year 8 would be 306.4. So that would be how that population would expand over that period of time. So our graphical solution, putting this into your graphing calculator, using a graphing calculator, it should look like this here when you graph this sequence. Next, graph the sequence. So this is your graph of that. You can estimate the last 5 years of the sequence as follows. Here it would be here. So again, if you put that into your calculator and you go in the table, you can see these values, these approximate values as well in your table, or you can go into your actual graph and then use your trace to find these same values here. Okay, let's try this one here. Deposit $5,000. It's made an account that earns 3% interest compounded quarterly. The balance in the account after n quarters is given by this function here. Compute the first 8 terms of the sequence. So here is our function. There's your n there. 1, 2, 3, 4, 5, 6, 7, 8. So when we do that here, we end up with this here, with these values here from our output when we plug into that function, and then computing the 40th term. That's up to you. That's part 3 of 8.1, students. Thank you very much.